right angle. So the pilot sitting in the back, the rover driver, is telling it, we want you to go to that area. But use your good judgment. Don't drive over a cliff to get to the area, right? So it's got smarts inside. Yeah.
So if I tell it to go left, will it take 30 minutes before I know it went left?
Exactly. Until you see the first sign. So it's, if this was on the moon, it would take about 1.5 seconds for the signal to get from the Earth to the moon. So you could almost do it in real time on the moon. It's almost like putting on goggles and doing a video game. But this is a video game where there's a 30-minute time delay till you get the feedback. So the people running this and planning this mission designed all this ahead of time. So it tells you there has to be a lot of computer smarts inside, software and special robotics. Very good question. So how do you land on Mars?
How hard is it to land Curiosity on Mars? On a scale from 1 to 10, landing on Mars is a 20. Curiosity is the biggest, most capable Mars rover yet, and needs a new type of landing to reach the ground safely. In this 7-minute trip to the surface of Mars, we have to slow down from over 13,000 miles an hour down to 0. Hundreds of things have to go just right. Curiosity must hit the atmosphere at just the right angle, endure extreme heat from friction as it descends through the atmosphere, open its parachute at just the right time, use radar to know exactly how high it is, free itself from the parachute, perfectly fire 8 rocket engines to slow final descent, drop down dangling on 4 cables, lock its wheels into place just before landing, and cut the cables right at the moment of touchdown. And even if we do everything right, Mars can always surprise us. It's a big challenge, but a big opportunity to help unlock the mysteries of Mars.
Yeah.
How did they assure that there wasn't going to be any death storms, that kind of stuff? I'm sure it was more calculated than just saying, I hope it doesn't happen.
Not really. Really. I mean, it's a really good point. Another thing to Google, Google 7 minutes of terror. Okay? There's a great video on YouTube. The Mars team, it's called the Mars EDL team, Entry, Descent, and Landing. It takes 7 minutes. That whole process from when you slam into the top of the atmosphere to when you actually land takes 7 minutes. We won't know until 15 minutes after it landed whether it survived. So when you get the first signal that it hit the atmosphere, it actually landed 8 minutes ago, but you don't know. So we don't have weather stations. We can't predict. There was a target area. And it turns out that it landed pretty close, and I'll show you in a couple charts where the target area was and where it really landed. It was almost like a perfect bullseye. Pretty amazing. But still, hitting that spot and hitting it where there's no wind gusts, where there's no dust storms, they designed the system to survive most possible windstorms, most possible dust, but still you don't know if it ended up landing and there's a boulder and then a wheel hits and the boulder's big enough it could flip over, and it didn't have the ability to turn itself right side up. So, we had pictures that were pretty good, but so that's it's really good design and some luck. I mean, so yeah, you hope. you can't predict. I mean, like an airplane coming into an airport, if there's really bad winds, they can wave off and you land at another airport. I mean, you can do that on Europe, but there's no way to do that. Yeah. So here's another view of the whole process. Really is pretty amazing how it worked, and it worked perfectly. These aren't pictures. These are sketches of what it looked like. So you can see this is it's called the sky crane. The shell sit on top. The shell popped off. And now it's lowering the actual rover toward the surface. And this cable was, I think, about 100 meters long. So this ellipse is actually the actual target area, and that's where it landed. Pretty amazing. Previous landings, They were lucky to get within 20 kilometers of where they wanted to land, which is why they would land in really flat, plain areas. Trying to show you earlier, most of the landings were near the equator because most of the flat, kind of desert-like area is around the equators of Mars. If you go more toward the poles, there's more mountainous regions. So because it had rocket engines on the descent, it had radar, it had all these cameras, the rocket engines were able to maneuver. So if it's coming in and it takes an image and see there's the landing area and I'm not headed there, the rocket could tilt it and steer it toward where the area was. That's why they got a little more aggressive. Because here's a ridge, and there's a big drop off in there. So they were willing to take a risk to land close to that ridge. Yeah.
Why couldn't they have moved it, I don't know how many, a few kilometers to the left, or however many kilometers it is, and then they wouldn't have to worry about the ridge?
They could have. There was also, this is a trade-off. There was a risk. First off, the mission is led by scientists, okay? There was a chance that it could land and the motors not work, or the motor could break and it couldn't travel that far. So what they wanted to do was say this, when this was proposed, this was going to cost about $700 million, and when they finally finished building it was about $2.5 billion. So it's a very complicated, expensive project. They wanted to make sure that even if the motors died out after like a week or so, that they were still close enough to some scientifically interesting stuff that they got answers to some key questions. So scientists were pushing to get really close to the edge here, because this is where they thought there was going to be evidence, maybe better evidence of liquid water in the past, maybe even current water. The engineers were pushing them to go out over here, because the engineers wanted it to work. They didn't care about whether there was data. They wanted the thing driving around and working, because that's what engineers want to do. They want to make the machine work. So it was a series of compromises and debates. Selecting the landing spot is it's an interesting process. And every mission that lands on a planet, they go through these debates. The engineers want one thing, the scientists want something else. But you're right, they could have played it safe and landed further away.
How big is Mars in comparison to Earth?
How are they?
Like how big is Mars in comparison to Earth?
It's about like 65 or 70% of the size. It's close. It's reasonably close. The gravity is less. It's a good question. I don't know the exact number off the top of my head. Jim, we can't turn more light off. This is, we had, can you lower those?
Yeah.
Awesome. While Curiosity was descending, it was timed, some of the other satellites that we had orbiting Mars would be overhead while it was descending and landing. The reason was so it could relay data, and they were hoping that cameras on board the orbiters could actually see Curiosity descending. There it is. That's the parachute. It's in this way landing. It's a picture taken from a satellite orbiting Mars of a lander landing, coming down on a parachute. That's pretty. It's not an artist's drawing. That's a real photograph. It's just mind-boggling that they could plan it and get it. I think I have another one here. Yeah, there you see even better. You see the parachute and the rover beneath it as it's getting close to the beginning of jettisoning the parachute, and then the sky crane lowering is coming up. Amazing pictures. Here's a self-portrait after it landed. You can see how rocky the terrain is around the rover. You see the wheels. This is a real photograph. It's actually a self-portrait that was put together. There's a camera at the end of one of the arms, although you don't see the arm on this picture. This is a composite. This wasn't all taken at once. This is a mosaic of around 10 different photographs that were all put together. So it makes it look like somebody came up and took a picture of the rover, but actually it took a picture of itself. So this is a panorama. This is Mount Sharp, which is very close to the landing site. Here's kind of the base of the mountain. this is some of the area around the rover. These rocks are maybe 2-3 centimeters high. So these are, this is really close in. You can see the quality of the cameras. And here's a piece of, people call this hood ornament. There's a piece of metal. They weren't sure what this was when they first saw this. This doesn't look like a rock. This looks like something artificial, right? This is not something natural right there. Turns out it's a piece of the rover that embedded itself in the rock as they landed. For the first couple of days, people were wondering, was someone else here? And they figured out it was actually, because it went over and it did a spectral analysis made out of the same kind of titanium as the rover. And so, Are We Ready? This is one of my favorite cartoons. So this is Mars. Sojourner, this was in the newspapers in the U.S. back about 15 years ago, and the Martians are trying to make sure that the people on Earth don't know there's really thriving cities and stuff, so they're holding this mural up.
It's still there. Like, be true.
So we've talked about Mars. Now let's look at some other places. And so remember, we said we want energy and liquid water. So where else could there be liquid water? Well, liquid water could be on the surface, but it could also be liquid water under the surface. So here's like get an idea of the size of the Earth, right? And these are some other moons: Europa, Ganymede, Callisto, Titan, and Enceladus. And you can see here, in some, we don't know what's inside each of these bodies, but scientists from studying photographs and using cameras and doing spectral analysis, understanding the chemistry, what's in the atmosphere and on the surface, because we've flown by these bodies, have speculated what's inside. So these are some other interesting targets. So first I want to talk about Europa. Europa is a moon of Jupiter. And what we know about Europa is the surface is completely frozen ice. It's really cold. It's 35 Kelvin. It's minus 240 C. Very cold. But there are all these cracks and lines. Europa is rather close to Jupiter. Jupiter's a huge planet. And it has not a circular orbit, it's got an elliptical orbit. It means its distance is changing. And when we've taken photographs of Europa, we've noticed the lines are changing. The lines aren't all the same. These are cracks in the ice. So the cracks in the ice are changing. How would cracks in the ice change? Melting, cooling. Also, if you think about it, Jupiter is enormous, big gravitational field, closer, farther, closer, farther. What's happening to Europa? It's flexing. It's flexing.
The ice is breaking.
Ice is breaking. Like icebergs are breaking. It cracks, it's flexing. So when it's flexing, also what happens when something is flexing, there's heat being generated, right? When there's flexing, there's heat being generated. So what we think, so what we think is happening is that there's ice here, and it's believed, what we theorize is, under the surface of Europa is a liquid ocean of water. And it's heated and it's melted because of the heat of all the friction. Scientists have done the math, figured out for the lines to change that much, and you know how big the gravitational field is of Jupiter and of Europa. You figure out how much energy is created. There's easily enough energy to melt ice. So under the surface there could be a liquid ocean. So one of the things that we scientists would love to do is have something land on the surface of Europa, drill down through the surface, and deploy a robotic submarine. Because it's liquid water and energy. There's heat from melting. Life. Fish. There could be, might be guppies. Science fiction writers, you can imagine. Maybe there's a fish, a sea-based life who has no experience. They have no idea there's the rest of the universe, because their universe is just they're under the. Now, is this 10 meters or is this 10 kilometers or 100? No one knows how thick the ice is, and obviously you need to know how thick it is before you think about landing there, because you need to know how long your drill has to be. So this is one of the really interesting projects we'd like to do in the next 10 or 20 years is to well, maybe first send a mission whose job is to measure how thick the ice is, because then you got to do that first before you send the actual drill and submarine.
How would you measure the ice with drilling?
You can use radar from the surface. Different frequencies of radar, because radar waves can penetrate water. You can tell the difference between ice and water, so you can get a map of the surface. Maybe some parts have thinner ice than others, and see, is that the same area over time? Go, okay, that's where we want to land. So
cool.
So I mean, you can see. I mean, these are just, and the ice cracking is very different all over the surface. But it's a frozen ice ball that's squishing. To think of like a tennis ball. I mean, if you take a tennis ball and just constantly squeeze it, it will heat up, because you have to take into account the heat from your hand. But the ball itself, the material, is going to get warm because you're compressing it. And that's the difference in gravity induced by Jupiter. So I want to skip this. So Galileo is a satellite that was flying all around the Jupiter system. It was launched in '89, and so all these pictures were taken by Galileo in the 1990s. Titan. Now we're going to talk about the system of Saturn. There's two really intriguing moons in Saturn. One of them is Titan. And Titan is actually almost the size, actually it's larger than our moon. And there was a mission called Cassini that's still flying around the Saturn system. And the European Space Agency designed and built a lander, so it landed on Titan. And it's really amazing. They've, from flying by Titan, there are lakes on Titan that are they're not water, it's liquid methane. So it's minus 200 degrees. Methane is, what?
The local gas.
It's a gas that, like, cow farts. Okay. So if that's mostly methane gas. The point is, methane is produced by organic processes, organic materials. So Titan, the Huygens probe landed. This is a picture from the surface of Titan, and there's a mission that's being planned to actually land a boat, a small robotic boat, on one of the lakes in Titan. This is going to happen sometime in the future. We're not sure if there's life there. I mean, the point is there's a lot of amino acids. The organic chemistry of Titan the chemistry is very similar to what we see on the Earth, but there's no oxygen. But we don't see liquid water, but all the building blocks of life are there. Doesn't mean there's not water there someplace, but it's an intriguing place because there's a lot of organic chemistry going on in Saturn. Saturn is like 2 billion miles from the sun, so it's much cooler. We're 93 million miles, so it's much further away. Enceladus. This one has really surprised people. I call this Old Faithful on steroids. Old Faithful is a big geyser in Yellowstone. So Enceladus is a small moon. It's about 100 kilometers in diameter. And what we've observed, we flew by Enceladus, was this is a picture taken. These aren't the true colors, but there are these big jets shooting out of the surface. And this is, again, a very cold moon. It's icy. It's rock and ice, the surface. And we were curious about what's in those jets of looks like, of liquid being shot out. So when you look at the spectra, water vapor, methane, carbon dioxide, simple organics, complex organics, all the building blocks of life are shooting out of this small cold moon orbiting Saturn. Again, you think about the big picture. We just thought the Earth is special, and we're seeing all these other places where the building blocks are there for life. I'm not saying there's life on Enceladus, but it was a very surprising result. So Cassini is still doing so. That's a picture of the Huygens probe. You can see here's people standing next to it. Right? So I should have changed this chart because Curiosity actually landed. I gave this talk about 2 months before Curiosity's landed. With regards to Mars, the next step is what people want to do actually is bring samples back, is to land a probe on Mars that would gather samples and then blast off, bring the rocks back to Earth. As sophisticated as our robotic chemistry labs are that we can send, there are tests and things that only a human can do. You can't possibly carry all the equipment on a satellite, robotic satellite, and explore and get everything you need. So we really want to try to figure out how to do that. It's very expensive. So the hope is this will be an international mission with many countries contributing pieces. Europa we talked about. Europa is, the hope was to get a mission started sometime around 2022. If you launched in 2022, it takes about 8 years to get there. So it would arrive in 2030. There's no money to do that. The concept, there's one mission is called JUICE, Jupiter Ice Moon Explorer. Hopefully could launch in 2022 and arrive in 2030. So another thing about working in this business is you have an idea, it takes like 20 years for it to, if you're lucky for it to happen. So it takes a long time. It takes patience. Enceladus, there's a lot of really interesting ideas people have, but the scientists don't think it's as high priority as going to Europa. So unfortunately, even though we've got this moon shooting out all this organic stuff with water, we don't think anything is going to go to explore for 2030. So maybe you guys will be working on, one of you guys will be working on one of these missions. And Titan, the hope is to land in one of the seas, possibly launch in 20. That mission it didn't get selected. So there's interesting ideas on how to explore, but there's not money in the budget. So I'm going to close with the last chart. Is this is like really, you think about it, this is really an amazing time to be alive, because for thousands of years humans, like at night, would go to bed, lay down, look up at the sky at night and look at stars and wonder what's there. Is anybody looking back at us, wondering what are these? Are these just lights? Are these candles sitting up in the sky? What are these? And now we build these machines that send us back pictures and all this knowledge, and this is happening while we're alive today. I mean, it's really pretty amazing that we have all this capability to answer, not just to go there, but to send back and answer questions, which of course are begging more questions, which is about really what the whole science process is. And finally, to close and to tie up with what Shelley is teaching you, this stuff is bordering on science fiction, because in the science fiction written in the middle of the 1900s, 50s, 60s, 70s, people were speculating about finding life on Mars, Martians, the Martian Chronicles by Ray Bradbury, and we're exploring that place now. We got photographs. We got machines driving around, scratching rocks, zapping rocks with lasers. So we're exploring things that science fiction writers have been writing about for hundreds of years. So it almost makes me think, what's cooking in our heads now about the science fiction for the future, right? Because we're exploring science fact with what people thought only like 50, 100 years ago was science fiction. So we're making that stuff like science fact now. So it makes me think about what kind of sci-fi are people thinking about beyond now? And, what's future science fiction going to be like? So that's all I had.
Can you go back to the slide about, it's a long time ago,
Yeah, it's okay.
the rock that came from Mars?
Right, sure.